Hello, I'm Paul Wakim. I'm Chief of Biostatistics and Clinical Epidemiology Service at the NIH Clinical Center, and this is the second segment on hypothesis testing. And in this segment, we're going to talk about p-value and the Bayesian approach. And we're going to start with sort of a little bit of fun, an experiment. So here's what we're going to do. I've got two coins. This coin actually has two heads. It actually does have two heads. You know, you can get those online for something like $7. But it has two heads, and this coin is a regular coin. You can't see them because they're too far away. But this is a regular coin. Has head on the side, tail on the side. This one has two heads. So two coins. I'm going to put them in my hands, and I'm going to let you pick one hand. Okay, so you pick one hand. Okay, so I put the other one aside, and this is the coin I'm gonna be tossing. Okay, you don't know. I'm not gonna tell you which coin you picked, but that's the coin I'm gonna be tossing. So what we're gonna do is I'm gonna do an experiment where I toss the coin, and I come back and tell you the result of the tossing. Of course, you don't know the true state, and this is trying to mimic scientific research. You don't know the true state, but you see data, and based on data that you see, you make inference about the coin that we're tossing. So I'm going to toss this coin, and the question is, given the data, which coin am I tossing? The null hypothesis, sort of the default, it's the regular coin. It has head on one side and tail on the other side. And the alternative hypothesis is that it's the other coin, it's the two-headed coin. Okay? And so we have equipoise. What does that mean? It means that the coin is as likely to be the regular coin as the two-headed coin, because you picked and you had 50-50 chance of selecting one or the other. Okay, so again, the experiment, I'm just putting sort of a summary of what we're doing here. We have an experiment, we have two hypotheses. The null hypothesis is that it's the regular coin, the alternative is that the two-headed coin. But before I start, so I'm gonna do my experiment in my lab. I'm going to come back to you and say this is the result, and you're going to have to decide. Are you tossing the regular coin or are you tossing the two-headed coin? But you know, think of it this way. Your decision is extremely important, and it has major public health ramifications. So you know, either mistake is a huge mistake, has big public health ramifications. That's one. Two, the sooner a decision is made, the better. People are dying. And so, you know, we need answers as quickly as possible. And three, every toss, every experiment costs a lot of money and takes a lot of time. Okay? I'm trying to basically parallel real scientific research with this tossing of a coin. So it's important that you make the right decision. You need to make it as fast as possible. And every experiment is basically costing a lot of money and take a lot of time. So I go to the lab, I toss it once, I come back to you and I say, I tossed it once and I got one head. And the question is, are you ready at this point to make a decision? Would you reject H0? Would you conclude that it's the two-headed coin because I got one head out of one toss? Chances are that you wouldn't. It's just way too early. So forget the first experiment. This is important. Forget the first experiment. Let's say when I went to my lab, I tossed it twice. And I came back and I told you I tossed the coin twice and I got two heads. Okay? So would you now reject H0? Would you conclude now that it is the two-headed coin? Again, forget the first two experiments. Completely forget them. They didn't happen. I went to the lab, I tossed it 3 times and got 3 head. Are you ready to now conclude that I'm tossing the two-headed coin? And same thing with 4 tosses, 4 heads, 5 tosses, 5 heads, 6 tosses, 6 heads, and 7 tosses, 7 heads. So you can pause the video right now and stop and say, okay, ask yourself, how many heads would it take for me? How many tosses and how many heads would it take for me to say, okay, now I'm ready to make a decision or the conclusion that I'm tossing the two-headed coin? How many heads would it take? Ask yourself that question. And then, now, when you come back from the pause, look at this table and say, well, which one did you pick and what is the corresponding p-value? What is the p-value? The p-value is basically saying, if I were tossing the regular coin, what is the chance of getting 1 head out of 1 toss? It's 0.5. Now we're talking about 2 tosses. If I were tossing the regular coin, what is the chance of getting 2 heads? 0.25. If I were tossing the regular coin, what is the chance of getting 7 heads out of 7 tosses? 0.008. Okay, well, the data is the data. The data, we can't say, oh, but you didn't get really 7 heads. I did get 7 heads. So if the data is the data and the probability of getting the data under an assumption is very low, what are you going to question? You're going to question the assumption. So the whole thinking is, if the probability of getting 7 heads out of 7 tosses is 0.008, if I were tossing the regular coin, probably I'm not tossing the regular coin. It seems like I'm not tossing the regular coin. So you question the assumption of tossing the regular coin. And that's what the p-value is. And I'm going to go over the sort of the more formal definition. But the interesting part for yourself is this corresponding p-value, the one that you decided you will decide, this is when I decide that I'm tossing the two-headed coin. How does it compare to this the commonly used p-value of 0.05? Okay. So, let's kind of think about the whole thing. So we have a hypothesis. The null hypothesis, it's the regular coin. The alternative is the two-headed coin. We did 7 tosses, got 7 heads. P-value is 0.008. Conclusion, we reject H0. Okay. Now, have we proved that it's the two-headed coin? No. It could still be that I'm tossing the regular coin and it just, by chance, happened 7 heads occurred. We haven't proved that it's two-headed coin. Is 0.008 the likelihood that the results are due to chance? No, it is the chance. It's not the likelihood that the results are due to chance. It is the chance of getting what we got. Is 0.008 the probability that it's the regular coin? No, it is not. Is 1 minus 0.008 the probability that it's the two-headed coin? No. The reason I'm putting these is because these are all the misinterpretations of p-values, and they are pretty common. These interpretations are incorrect. So, what is the correct one? 0.008 is the probability of getting 7 heads if it is the regular coin. Not more, not less. That's all it is. And all the other interpretations are incorrect. So, what's the formal definition of a p-value? The p-value is the probability of obtaining a result as extreme, by extreme we mean away from the null hypothesis, or more extreme than the one obtained if H0 is actually true. Now let's talk about the Bayesian approach. The Bayesian approach is actually very intuitive. It's really how we think about things, how we go through life. How do we go through life? We basically know very little, and then we observe. And then as we observe, we update our beliefs. And then we observe some more, and we update our beliefs again. And so we move through life like that. We just learn, and update our thinking. Well, Bayesian has the same logic. You start with a prior belief, what you think is happening. You don't know, that's what you think. It could be very loose, vague, but that's what you think. And then you get data. And you use the data and the prior belief, you put them together to get a posterior belief. In other words, your updated belief. So you have an old belief, combine it with data, and now you have an updated belief called the posterior belief. But then the posterior belief becomes prior belief. So as you're moving, you're learning and updating, and learning and updating. So the posterior belief becomes the prior belief. And then you get new data, and then you update, and you get a posterior belief, which becomes a prior belief, more data, posterior belief. And so on, until in life you never stop, but in clinical trials and in biostatistics, you do biomedical research, you do stop when there's enough posterior belief to conclude efficacy or futility. And this can be at a patient level. So every step that I'm showing you on the slide could be at the patient level. So every patient comes and you update. Or it could be with group of participants in a clinical trial. So the first 10 you update, and after that another 10 and another 10. Or it could be clinical trials. The first clinical trials, you get data, it becomes prior. You have another clinical trial, and you get data and you update. So the difference between the Bayesian and the frequentist approach is that the Bayesian think of the probability of getting ahead, P, as a variable. So to say it's a regular coin, what does it mean? It's the same thing as saying that the probability of getting ahead is 1/2, right? I mean, if I tell you I have in my hand a regular coin, it's the same thing as if I told you the probability of getting ahead is 1/2. P is 1/2. Regular coin and P is 1/2 are the same thing. And the two-headed coin and P is equal to 1 is the same thing. So we're talking about the same. So Bayesian approach sees P as a random variable. The frequentists say, no, once you pick the coin, and that's the one you're tossing, there's no probability, there's no distribution, there's no chance. You either have the regular coin or the two-headed coin. There's no probability. The Bayesians say, well, but yes, I picked it and it's determined, but I don't know what it is. And therefore, I'm going to put a probability to it. So, saying what is the chance that it's the regular coin is the same as saying what is the chance that P is 1/2. And saying what is the chance that it's the two-headed coin is the same as saying what is the chance that P is 1. It's the same thing. So if we start with the prior belief that both coins are equally likely, remember we selected one of the two coins randomly. So we start, the prior belief at the very beginning is that it's basically the probability, and you may not be able to see this, but you'll get the sense of it when I complete the slide. But remember, P is 1/2, it's the same as saying it's the regular coin. P is equal to 1 is the same as the two-headed coin. And at the beginning, P is 1/2. We have a regular coin, 1.5 chance of having the regular coin and 0.5 chance of having of tossing the two-headed coin. So P here is a variable with a distribution, but it only can take two values, 1/2 or 1, because it's either the regular coin or the two-headed coin. So what happens in the Bayesian approach, we're going to update the distribution of P as we're getting data. And that's really the difference between the two thinking. So now I'm tossing once and I get head, and I'm going to update that distribution. So now the chance that it is the two-headed coin has just increased a little bit, and the chance that it is the regular coin has decreased a little bit with one toss. And then I toss again, and I get head, and I update. And it goes up. And again, 7 times. So you can see after 7 tosses and 7 heads, the distribution of P now is clearly with the two-headed coin, in favor of the two-headed coin. So you can see with every toss we've updated. Now notice the difference between the two situations. I said in the first scenario, I was going back to the lab, forgetting the other experiments and tossing it 5 times, then going back, tossing it 6, then going back, tossing it 7. Here, I'm doing it one after the other, sequentially. So, when you update the probability, these are the numbers. So, with the first toss, the probability, the Bayesian posterior probability of the regular coin is 0.333. And after the second toss, it's 0.2. After the third, etc. And after the 7th toss, the probability of the regular coin is 0.008. And I want to make it very clear, and I may repeat it again in a minute, very clear. In here, we are talking about the probability that is the regular coin. Remember, when we were talking about p-value, we said specifically, explicitly, it is not the probability that it is the regular coin. So very different concepts. So what was actually wrong with the p-value is actually correct interpretation here. There are different concepts. They are calculated differently. They have different statistical definition, mathematical definition. So they're completely different concepts. It's not the same formula that's giving you 2 answers. No, different concept. It's important to distinguish the two. So the Bayesian approach, again, a regular coin is P is equal to 1/2, two-headed coin is P is equal to 1. If we start with the prior belief that both coins are equally likely, after 7 tosses and 7 heads, 7 tosses the experiment, 7 heads the data, we do say, now, we're 0.8% sure that it is the regular coin, and it is 99.2% sure that it is the two-headed coin. Something we did not say. We said it was wrong to say this when we were talking about the p-value. So I'm doing this with hesitation because I'm going to put the 2 tables side by side, and there is a little bit of a danger with that because these 2 tables. There are 2 tables you've already seen. One when we were talking about the p-value. One when we were talking about the posterior probability. They are very different tables. The first thing to notice on the left it says number of tosses. On the right it says toss number. On the left it is you remember we go to the lab, we do it once, then we forget about the first. We toss it twice, we get 2 heads. We toss it 3 times, we get a 3 head. On the right, the table on the right, the Bayesian approach, is the toss number. We do 1, we update. We do the 2nd, we update. We do the 3rd, we update. So right there, they're different. And also, they're, of course, different in the p-value. The p-value is not the probability that it is the regular coin, as we discussed. In the Bayesian approach, it is. So you're saying, well, why am I putting them side by side? Because I think it's interesting to see that the numbers are not that different, even though they're different concepts. Calculated differently, but you can see that it's interesting to see that the numbers are fairly close. Again, remember the p-value is not the probability that it's the regular coin. I just want to emphasize this as much as I can because that's exactly the misinterpretation of the p-value. So these are the references. So in summary, the p-value is the probability of obtaining a result as extreme or more extreme than the one obtained if there is no difference, if in fact the reality is that there is no difference. And the Bayesian approach is gaining popularity as being more intuitive and is definitely worth considering. And my questions to you is to true or false. Failing to reject the null hypothesis means that the null hypothesis is true. The p-value represents the likelihood that the results are due to chance. The p-value is the probability that the null hypothesis is true. True or false. Thanks for watching.